Okay, so I'm going to forego reviewing addition, subtraction, determinants, and all that stuff because we've already done that enough. And you've done addition and subtraction before, so we'll talk about some of the more important stuff, like the multiplicative inverse. I'm sorry, the multiplicative identity matrix. Which we usually call I. And it's defined as an n by n matrix with a diagonal of 1s and 0s everywhere else. So this is an n by n matrix. It's called a multiplicative identity matrix because if you were to multiply a matrix with I, you would not change the matrix that you are multiplying it to. Hence, multiplicative identity. So that leads us to saying that A times I is the same as I times A, which is equal to A. And again, this is for also an n by n matrix. In addition, if we were to take the identity matrix times some matrix X, we will get the same matrix X again as long as X is an n by 1 matrix. Okay, these are things that are easily verified if just through experience. If you want to prove them, knock yourselves out. Nothing too fancy yet. Okay, a zero matrix. Along the same lines as what our Calc 3 textbook did with vectors, sometimes you'll see a bold 0, which will indicate that we have a matrix with zeros for all the entries. And this goes for any size, which leads us to the property that if A and O, or 0, if both of these matrices have the same dimensions, so let's say they're both m by n, then adding the 0 matrix with A and vice versa will also result in an identity. Okay. Let's see. Associative property of multiplication is exactly what you would expect it to be from earlier. If you have 3 matrices that you are multiplying, you could multiply B and C together and then A, or A and B, and then multiply it with C. Nothing new there. The distributive property with matrices looks something like this. If we have A times the sum of matrix B with C, that is the same as A times B plus A times C. However, this is not necessarily equal to BA plus CA. Might be, but not necessarily. Which is why this is also an important property. If we have B plus C and then times A, then this has to be exactly BA plus CA. Looked like Rick almost got taken out over there coming in. All right. So order in which you multiply matrices, very important. Make sure you just remember that. Any questions so far? This is stuff that, through experience, several years back, you probably have seen or know at one point. Just make sure we have that out there. And we'll see how far we can get. All right. Transpose. Maybe this is something you haven't seen too much of. For A, which is M by N, so let's say we have something that looks like this. A11, A12, etc., A1N, A21, A22, and so on, all the way down to mth row, so AM1, AM2, and then AMN. So these are just the entries of the matrix. This is a standard run-of-the-mill M by N definition. The transpose of A looks something like this. A11, A12, and so on, down to A1N. All you're going to do is take the rows of A, and what we mean by transpose is now the rows become columns and vice versa. So the easiest way to do that is to literally just take first row, make it a column. Second row, make it the next column. That's all we mean by transpose. So it should look something like this. Upper left is always the same, and bottom right, yep. So we'll do a quick example. Sometimes it's easy to just see it with a numerical example here. So let's say A is a 2 by 3, 2, 1, 3, 6, 2, negative 5. The transpose would, instead of a 2 by 3, be A. What? Good. And now this is a 3 by 2. And again, yeah, 2 top left, negative 5 bottom right. those remain the same. But again, the easiest way to do it is just take column 1, take row 1, make it column 1, take next row, make it column 2, and just keep doing that. Okay? So I don't know if you've seen this before or not. Maybe you saw it in the calculator when you were fooling around with the matrix options and you saw this little T sitting there. That's what it would do. Okay? All right. This will be a big one for us. The multiplicative inverse of a matrix. So we're going to start by assuming that A is going to be n by n. So let A be an n by n matrix. If there exists an n by n matrix B, we'll call it, such that A times B or B times A results in getting the identity matrix, then we call B the multiplicative inverse of A. And we call B another name, we just call it A inverse as well. Here's a definition that we'll need. If A is n by n, and the determinant of A does not equal 0, then we say A is non-singular. If the determinant of this square matrix does in fact equal 0, then A is singular. Here's an important side note. An n by n matrix, let's say A, has an inverse if and only if A is non-singular. In other words, the only way that a n by n matrix will have an inverse is if the determinant of A does not equal 0. And if you're not familiar with how to find the inverse of a matrix, we're going to go through that for a 2 by 2, 3 by 3, and so on, so you get an idea of how to do that, and it'll be very clear why the determinant needs to be not equal to 0. Okay, so here's a formula to find an inverse. So we start by assuming that A is, of course, a square matrix. And non-singular. So the determinant is not equal to 0. In addition, we're going to introduce some new notation. We're going to let C sub ij equal negative 1 to the I plus j times mij sub ij, where m sub ij is the determinant of the n minus 1 by n minus 1 matrix obtained by deleting the ith row and jth column from A, I should say. And following this pattern, the definition for an inverse is then 1 over the determinant of A times the transpose of C sub ij. Okay. This probably seems a little weird, the way this is written out. It'll make sense, I promise. Let's say A is a 2 by 2 matrix Here's how we can find it using this idea. So first, to find the inverse, we find the determinant of A. We do 1 over that times the transpose of this operation up here. So we haven't transposed it yet. So all we're going to do is follow what this says here. So we look at this first position, first row, first column. If we eliminate what's in the first row and in the first column, then all that's left is a 1 by 1 matrix. Does that make sense? This little guy down here. The determinant of a 1 by 1 matrix is going to be itself. Okay, so that's going to be A22. Now over here, doing the same idea, we eliminate this row, this column, what's left? Which entry is left if I wipe out first row, second column? A21. I'll fill in some negatives here in a minute. The next entry would be, if I second row, first column, so eliminate here, eliminate there, what's left? Just A12. And now here, if I eliminate second row, second column, the only thing left is A11, and again the determinant of that is itself. Okay. And now we just have to adjust some negatives here. According to this, we just take -1, I plus j. So here we were in first row, first column. If I add those two together, what exponent is that? Just 2. So then this entry is going to be positive. Here in the first row, second column, this is a negative exponent because it's going to be an odd power. So we put a negative here. Similarly, down here, we put another negative sign. And then second row, second column's good. And then the final step is to go ahead and transpose. So we have 1 over the determinant of A. And now what's the transpose of this matrix? So here's a formula which you may have been taught at one point. Here's this mysterious inverse matrix. Here's how you find it, right? It should look familiar if you did any work with that. Or if you did math team for a while, you probably have seen this floating around somewhere. Okay? So you could either memorize this formula or just kind of repeat the process. So let's do a quick one. Find inverse for, let's say, A equals 2, 3, -3, -4. We do 1 over the determinant. What would the determinant of A be? Everybody see where we get 1? 8, -8 plus 9 is 1. And now we can kind of go through the same process here or use the formula. It's really up to you. If you use the formula, we just look at second row, second column. So that's -4. And then we do the opposite of first row, second column. So that's going to be -3. Opposite of second row, first column, so 3. And then we just put down first row, first column, so that's 2. So this is your inverse. Which means that if you were to take this matrix times this one, you would get what? What would A inverse look like? I. In this case, it'd be 1, 0, 0, 1, right? Okay. What negative sign? We already did that. Because we took, right, this is first row, second column, so here we did the opposite of that. Okay. So here I'm just using the formula, which it's easy to remember for a 2 by 2. Or if you just remember the process, which again, it's kind of weird, but you'll get used to it. We'll do it for a 3 by 3. So you can kind of see how it works. All right, so say we have to find the inverse for A equal to 2, 1, -2, 4, -2, 0, 0, 3, negative 1. First, let's go ahead and find the determinant of A. Which, it's been a while. Two times the determinant of 2 minus 0. Minus negative 4, and it would be minus 0. Plus, nope, minus 2 times 12, right? 12 minus nothing. So the determinant of A is 4, 4, negative 16. Okay, so there's our determinant. And now here's the best way, I think, to organize it. Okay, we're going to go through and find all the C sub ij. So we're going to go through and find C11, 12, 13, 2, 1, 2, 2. You know, it's a 3 by 3 matrix, so we'll do it for each position. Okay? So C11 is equal to what? What do we do? We eliminate first row, first column. So wipe away first row, first column. What little 2 by 2 is left? So I'll actually write it out. Just negative 2, 0, 3, negative 1. And I'll put in all the negatives later. Let's just find the determinants. Okay? What's the determinant here? 2. Okay, we'll do the same thing. C12. So this is where it gets a little weird because we're still okay. So eliminate first row, second column. We have 4, 0, 0, negative 1. And that determinant is negative 4. I should probably write a little smaller. C13. We have 4, negative 2, 0, 3, and that determinant is 12. Okay, do you guys see where I'm getting these from? Due to determinants. Either way, it doesn't matter. I like to find the determinants, and then in the end, I'm just going to go whatever has an odd sum, just do opposite. Okay? So I'm going to go ahead and do C21 now. So wipe away second row, first column. What's left? Or, I'm sorry, second row, first column. What's left? One, negative 2, 3, negative 1. Yes. Determinant of that little 2 by 2 is 1 minus 1 plus 6. Negative 1 plus 6 is 5. C22. This is the one I was thinking about. Eliminate second row, second column. We have 2, negative 2, 0, negative 1. And that is negative 2 for the determinant, and then C23. So eliminate second row, third column. We have 2, 1, 0, 3, and that's just 6. Repeat for the last position, last row. So C3, 1. Eliminate third row, first column. We have 1, -2, -2, 0. So that's going to be 0 minus 4, so -4. C3, 2. If I'm going too fast, slow me down. Third row, second column, we have 2, -2, 0, -1. Determinant is -2. Oh wait, that's not right. Let me redo that. Third row, second column, 2, -2, 4, 0. So that's going to be 8. And then C3, 3. So third row, third column, 2, 1, 4, -2. That's -4 minus 4, so that's -8. Okay. So now the last thing that we haven't done yet, and again, you can do this however you want. So after we find all theCij's, all we've done is find the Mij's so far, right? We need to now adjust the sign. So easiest way to do that is to just add up the positions, 1, 1, 1, 2, 1, 3, and so on. If it's an even exponent, that's obviously going to stay the same. If it's an odd exponent, then you're going to do the opposite. So for 1, 1, what do I do? Leave it. 1, 2, this becomes +4. So anything that has an odd sum here, you do the opposite. So that's good. 2, 1, we're going to make negative. Anything I'm changing, I'm going to put a green circle around it. Okay, so these are the 4 positions that switch out. And now, the inverse of A is 1 divided by the determinant, right? So 1 over determinant, that's 1/16. We'll make it negative from there. And then you can do it now. This is the transpose of this, and this doesn't look like a matrix, but if you ignore all the work and just focus on the numbers, the entries 2, 4, 2, 4, and 12. Okay, this row becomes the first column of the inverse. This next row becomes the next column of the inverse. And the last row becomes the last column of the inverse. Okay? And then obviously you can clean it up. That's going to be -1/8, 5/16, 1/4, -1/4, 1/8, 1/2, -3/4, 3/8, and 1/2. Okay. Any questions on this? Okay. This procedure works for any order. Sorry, I'm thinking diffq. Any size matrix. So 2 by 2, 3 by 3, 4 by 4, and all that stuff. Okay, so you'll learn more about that in linear algebra if you take that next year, and there will be other methods for higher order, or sorry, for larger size matrices. This is obviously not the most swift technique, but it does do the job, and it always works. Okay. As far as what's left today, just a couple of quick well, you know what? I'll just do it this way. Calculus on matrices. Do what you would expect. I'm not even going to do any examples. Which means that if you're integrating a matrix, what you're going to end up doing is what? Integrating each spot. Take the derivative of a matrix, differentiate each entry. Does that make sense? Okay. That's really all that needs to be said there. Tomorrow we'll pick up. I am out of time, right? Yeah. Tomorrow we'll pick up with some systems and starting to do some more heavy-duty stuff. And I hope we can get to eigenvectors and eigenvalues, which is a big, big, big theme for us. All right, I'll see you guys tomorrow.